Hello and welcome back to Physics 252. This is Monday's lecture for week 10, covering the last three sections of chapter 23 on inductance, so sections 23.5 to 23.8. So we have this very short list of passive components that make up the fundamental building blocks of any electrical circuit. We've already talked about two of them. So you know about resistors that resist the flow of current, and capacitors that store electrical energy in the form of charge. So we see that capacitance is really just a proportionality constant between voltage and charge, just like resistance is a proportionality constant between voltage and current. This is another form of Ohm's law, if you remember. And the two new ones that we're going to be talking about today are the inductor and the transformer. So an inductor looks like that. It's just a coil, and the symbol is a little curly line like that, and the symbols L and the units are henries, or H for henries. And we see that just like capacitance being a proportionality constant between charge and voltage, inductance is the proportionality constant between flux and current. And I've expressed, I've just divided the top and the bottom by delta T in this case. So delta Q over delta T divided by delta V over delta T gives me current in the numerator, because current is dq dt. And so then I have this relationship between capacitance and current, C equals I over dV dt, or I equals C dV dt. So that tells us that capacitors resist changes in voltage in a circuit. And similarly for inductance, we'll see how we derive this in a little bit, but this is just another form of Faraday's law. We see that inductors resist changes in current in a circuit. So capacitors resist changes in voltage, inductors resist changes in current, and resistors just resist the flow of current. And then finally we have a transformer, which is two inductors on a common core. They kind of look like this. There's just a square piece of metal with wires wrapped around both sides. They don't look like that. And they're used to step up or step down voltages. For example, to get the voltage from Mount Storm to your house, the transmission lines, as we discussed, are at 30,000 volts or higher, and your house voltage is only 120 volts. So we need to step that down with a transformer. All right, so how do we come up with these relationships? I want to talk about that for a second. First of all, we have to know that flux is proportional to current. And the way we know that flux is proportional to current is we know that flux is the product of area and magnetic field. And magnetic field is proportional to current. To convince you of that, I've just written Ampere's law, and we've seen this before, but I'll derive the magnetic field in a solenoid again a little bit later. But using Ampere's law, you can show that the magnetic field in a solenoid is the permeability of free space, mu naught, times the turns per unit length times the current. So it's proportional to current, right? Because these two are constants. And for a wire, we know that we just take our Amperian loop as a circle with perimeter 2 pi r. So B 2 pi r equals mu naught I enclosed. And if I divide both sides by 2 pi r, I get B equals mu naught I divided by 2 pi r. So again, magnetic field is proportional to current. Okay, and this is the definition of flux. In the case where magnetic field is constant across that area, which we often do by design, then flux is just the product of magnetic field and area times the cosine of the angle between the two. So flux is proportional to magnetic field B, and B is proportional to magnetic field I. That means that flux is proportional to I. Alright, that means that we can take Faraday's law of V equals minus dphi dt and write it in a different way. Right? If flux is equal to some constants times I, then I can take those constants out of the derivative, and I just get V equals minus a bunch of constants that just depend on geometry times di dt. Alright, now if I just redefine all these constants as L, this is my proportionality constant, basically between voltage and the changing current, then I have this definition for inductance, and the units, the SI unit for inductance is the Henry, named after this guy, Joseph Henry. Finally, an American, right? So far we've been talking about Europeans mostly that have given us the pillars of electricity and magnetism and classical mechanics, but now finally we have an American that's contributed something substantial. He actually discovered a lot of the same things that Faraday did, he just didn't publish them. Right, so Henry is a volt-second per amp. All right, even if we don't have a coil in a circuit, something that gives us a lot of turns, we have this effect that you already know about from Lenz's law. Imagine for a second that that inductor isn't even there, right? And we've got this switch open, and we just closed this switch, so we have a current that's going clockwise through this resistor, right, out of the positive terminal of the battery through the resistor. And if we use the right-hand rule to determine the direction of the magnetic field that's created, you put your fingers in the direction of I, and your thumb will point in the direction of the magnetic field that's created by this current loop, and in that case that's into the board. Well, Lenz's law says that we are going to induce a current that opposes the change in magnetic flux. Well, magnetic flux is increasing into the board. So to compensate for that, we have an induced current that's going counterclockwise, which will create a magnetic field out of the board. So it's almost as if there were another battery, and I've written a little battery in this circuit here, even though there's not a physical battery. It's as if there's another battery there that's creating this current that opposes this current. And if you have some, let's say 10 volts here, and your back EMF is 8 volts, now your total current is going to be a little bit less because of this back EMF. Right? It's also called self-inductance. Now, so this happens for any real circuit, because any real circuit is going to have, a wire basically has some inductance. You already know that because you know that a wire creates a magnetic field around itself, and inductance is just a number of turns, which would be 1 for a wire times mu naught I over 2 pi r divided by I, so just mu naught over 2 pi r. So even a wire, single wire, has some inductance. All right, let's figure out what the inductance would be for a solenoid. So now when you have a bunch of turns, I'll just put this picture back up to remind you of how we calculated the magnetic field in a solenoid using Ampere's law. Here's in this little pink rectangle shows our Amperian current loop, and we remember that the magnetic field created by the solenoid looks like a bar magnet. Right? We have the magnetic field from each of these little current loops reinforces in the center, so the magnetic field is really strong inside, and then it reconnects on the outside just like a regular bar magnet would be. So the important thing to note here is that the magnetic field is perpendicular to our path on the sides. And remember, when you take the dot product of two perpendicular vectors, you get 0 because the dot product is equal to the magnitude of B times the magnitude of L times the cosine of the angle between them. And the angle between them is 90 degrees. The cosine of 90 degrees is 0. So the dot product is 0 on the sides. And if you take this dashed line sufficiently far away from the bar magnet, then the magnetic field is approximately 0. So that means the only contribution to this B dot dl integral is this length here inside the solenoid. So then the left-hand side would read B times L for length equals mu naught I enclosed, and I enclosed is just n, the number of turns, times the current in each loop. So you have BL equals mu naught I n. And you divide both sides by L, and you get B equals mu naught Ni, small ni, where the small n is just a big N divided by L. Alright, so now we apply this formula again. Inductance is the flux divided by current times the number of turns, and substituting our value for a magnetic field in a solenoid that we got from this, mu naught big N over L times I, and dividing by current, we get this relationship for inductance. So you can use this same method to calculate the inductance of anything else where you know the magnetic field. Okay, next thing I'd like to talk about is RL circuits. So this is very similar to a discussion that we had about capacitive circuits. Remember, RC circuits. We know that depending on the resistance and the capacitance of a circuit determines how long it takes to charge or discharge the capacitor. And something similar happens with an inductor. Except now, instead of storing charge, we're storing magnetic energy. Right? We're storing current, basically. So imagine where we have this situation where we open this little shunt switch and we close the power switch. So we just have current that's going from the positive terminal of the battery through the inductor, through the resistor, and back to the negative terminal of the battery. So following this loop clockwise like this and starting at the negative terminal of the battery, I have this expression for Kirchhoff's loop law. So minus V naught, because I start at the minus terminal of the battery, plus the voltage drop across the inductor, which is L di dt, right? V equals L di dt for the inductor. And V equals IR, which is Ohm's law, tells us the voltage dropped across the resistor. So I just sum the two voltage drops across these components, and I know they have to be equal to the voltage supplied by the battery. Now, I've rewritten this a little bit, right? Divided both sides by R and then multiplied by minus 1, and then made this substitution, U equals V naught R minus 1. and then if I take the derivative of U, I know it's equal to the minus the derivative of I because of this minus sign. So if I just make these substitutions, I can write the expression like this, and then bringing the L over R du dt to one side and dividing both sides by U, I get this form, which looks like something you've probably already seen, right? This is a differential equation where all of the variables and the derivatives are on one side, and all of the other variable and its derivatives are on the other side. And we can solve this easily just by taking the integral of both sides. So the integral of du over u is the log of u, and the derivative of a constant dt is just a constant times time. And don't forget your integration constant, because when you take e to both sides, you have e to the log u, which is just u, equals e to the minus r over lt plus a constant. But if I have two terms summed in the exponent, that's the same thing as multiplying the two bases together with those terms. So this would give me e to the minus r over lt times e to some constant. But e to some constant is just another constant, so I'm calling that constant mu naught. And then I flip this upside down and put it in the denominator, because I'd like to write my exponential expression in terms of a ratio. Some time constant, which is going to be in seconds, in the denominator. And then one last thing I need before I arrive at this final equation is the initial value of mu naught. I know that in the beginning, right before I closed the switch, there was no current in the loop. So the instant I close that switch, the current in the loop is 0. So that means that mu naught is just V naught over R. So now substituting back my original expression for U, I get this expression for I. So probably you've seen this before, right? This is just like the remember function for charging of a capacitor, except now it's the remember function for charging of a inductor. So it looks like this. Right, so this C is the time constant in this case, right? So we see that decreasing the time constant makes the inductor charge up faster, and increasing the time constant makes it take longer for it to charge. So you know the way to increase the time constant, since the time constant is L over R, is to increase the value of inductance or decrease the value of resistance. And then I naught is just a scaling factor that tells us what the equilibrium value of the current is going to be. Okay, now let's look at the discharge situation. Here I'm going to open the power switch and close this shunt switch. So effectively we're taking this battery out of the circuit. So it's the same expression for Kirchhoff's law, loop law, except now there's no battery, so I'm just X that out, and I have just this expression left, which is very easy to separate and integrate both sides, and you just get I equals I naught e to the minus t over tau, which is just like the forget function for capacitor discharging. So that's this, right? And again, if I change the value of the time constant, if I increase the value of the time constant, it takes longer to decay to 0. If I decrease the value of the time constant, it takes a shorter amount of time to get to 0. And I'm just going to set this to 1 for convenience sake, because I think I've mentioned this a few times, but probably you've talked about this in your statistics class, right? After one time constant, so this is 1 second in our case, we get to a value that's 36 point something, about 36% of our original value. And after 2 time constants, we're at 13%. 3 time constants were 5%. And at 5 time constants, we're less than half of a percent. All right, the energy of an inductor. I'm using a different symbol for energy now. Before we've used PE for potential energy, or just E for energy. Your textbook uses U, and I think that's good because we've been using E for electric field in these chapters. So if I write power as the change in energy per unit time, the UDT, and I also remember that power is equal to the product of voltage and current. And we know now from Faraday's law, and using this proportionality constant L for V, we have P equals I times L di dt. So if I want to get the total energy, I have to integrate both sides of this equation. Right here I just multiply both sides by dt, so P dt equals du. Now if I integrate this expression, I get 1/2 Li squared. It looks very similar to what the energy was for capacitors, 1/2 CV squared. Or remember the energy stored in a spring was 1/2 kx squared. So, all right, the last passive component we're going to talk about is a transformer. And like I mentioned before, a transformer is just this ferrite core with windings on both sides. What makes it work is that the flux created by this is basically a solenoid, right? And the flux created by the solenoid are the same, because whatever flux goes through here travels through this ferrite core and goes through that. So they share a flux in common. So now you have a mutual inductance that's happening. They're coupled. And that allows us to do some neat things. Right? Here's Faraday's law again. Here's Faraday's law for the left-hand side, this primary side. V1 equals minus n d phi dt. And V2 is minus n2 d phi dt. But it's the same flux. The d phi dt is the same. So if I solve this for d phi dt, I get V1 over n1 with a negative sign. And if I solve this for d phi dt, I get V2 over n2 with a negative sign. So setting those equal gives me this relationship for the voltage. So now we see if you want to go from 30,000 volts to your house voltage of 120 volts, then you have to have 30,000 divided by 120 as the turns ratio between both sides of the transformer. It almost seems too good to be true, doesn't it? I mean, you could go the other way around. For example, you could start with 100 volts and you could end up with 30,000 volts. Well, we know that energy has to be conserved. What's happening? Well, if we look at the fact that the power has to be the same on both sides, and we know the power is equal to the product of voltage and current, then I1 V1 equals I2 V2, and we see that we have this inverse relationship between turns. Right? V1 over V2 is N1 over N2, but I1 over I2 is N2 over N1. It's the reciprocal. So as much as voltage is increasing, our current is decreasing. That's the trade-off. Okay, one last thing, and then we'll be ready for your homework problems 1 through 3. And that's root mean squared voltage. You'll see a reference to that in problem 3. So if you remember from our discussion of generators, when we were rotating a current loop through a magnetic field, we got this expression for voltage. This just comes from taking the derivative of BA cosine omega t. Right? It gives us sine omega t. So we have a mystery, I think, and that is, how is it that we're able to derive any useful work from a function whose average value is 0? Right? If I look at the average value of the voltage coming out of the wall socket, it's 0. Right? If I average this over a whole period, it's 0. Well, what we have to remember is that power is equal to the product of voltage times current, or using Ohm's law, I can get V squared over R or I squared R. So that means I need to square my current value. And so here's power equals I squared R, so in the black line. Now we can see that the average value of this black line isn't 0 anymore. It's 1/2, right? If you flatten this out, you average it out over a whole period, now you get 1/2. I mean, that's easy to see visually, but you can also take the derivative of your sine squared term, and if you use the trig identity, sine squared equals 1 minus cosine of twice this angle, so 1 minus cosine of 2 omega t, and then you integrate that, you'll come out with this 1/2. So if I rewrite this 1/2 Vmax squared as the square of Vmax divided by the square root of 2, I get the same thing. I hope you agree with that. So now I have power, the average power in one cycle is just VRMS squared over R. So it's a very convenient way to do power calculations, where instead of using the maximum amplitude of voltage, dividing it by the square root of 2 and so on, I can, remembering this formula, I can just do all of my power calculations the same way I would for DC, but substituting voltage, my DC value of voltage, for VRMS. So this is why we use it, and this is the value of VRMS. VRMS is just the maximum amplitude divided by the square root of 2. And that's it for inductance. So now you're ready to do problems 1 through 3. When you feel comfortable with that, please move on to the next lecture on chapter 24 about electromagnetic waves.